Watch a Formula One car snap through a high-speed corner. The suspension compresses under immense G-forces, channeling violent kinetic energy straight into the center of the chassis. In a conventional car, the engine sits inside a frame like a heavy passenger. In an F1 car, the engine is a rigidly mounted structural spine, the physical link holding the rear of the vehicle to the driver's tub. This dual purpose creates an immediate engineering contradiction. Aerodynamicists need the engine to be impossibly small and low to the ground, while vehicle dynamicists require it to be incredibly stiff to absorb cornering loads without flexing. The FIA regulations force this squeeze into a strict mathematical box, mandating a minimum engine weight of exactly 95 kilograms and a center of gravity no higher than 165 millimeters. Compressing a 1,000-horsepower power unit into these hyper-compact dimensions triggers a cascade of secondary physical failures deep inside the engine block. Winning on Sunday relies on surviving this dimensional squeeze through sub-millimeter fluid dynamics and microscopic metallurgy. Dropping the overall center of gravity is an absolute prerequisite for cornering speed, but achieving it requires a radical change to the internal architecture of the engine block. The only way to lower that center of mass is to drop the heaviest rotating component, the crankshaft, deeper into the bottom of the crankcase. This creates an immediate spatial crisis. Lowering the crank forces the spinning metal counterweights dangerously close to the inner walls of the engine block. At 15,000 RPM, air and oil in this shrinking gap become a viscous hurricane. This Honda data maps radial gap clearance against mechanical friction loss. As clearance drops below 3 millimeters, oil agitation causes an exponential spike in friction. To buy back that critical clearance, engineers bolt ultra-dense tungsten alloy weights directly to the crank, shrinking the counterweight radius to exactly 58.55 millimeters. The aerodynamic advantage of a lower center of gravity comes at a price. It breaks the internal fluid environment and forces a complete redesign of the engine's oil management. Clearing that tight crankcase requires highly aggressive scavenging. Teams install independent dry sump pumps at the front and rear of every individual chamber to instantly vacuum oil out of the block. While those pumps pull oil out, a feed pump must simultaneously blast oil into the spinning crank pins at 900 kilopascals to overcome the massive centrifugal forces that actively reject the fluid. At 12,800 RPM, centrifugal force flings fluid outward, generating negative pressure bubbles that cause oil pressure to plummet. The solution? Split the thick rotor into two 8mm rotors. Modifying the suction port to pinch shut as it fills traps the fluid, restoring pressure. But driving these dual rotors at extreme speeds induces a massive tertiary torsional resonance inside the pump's driveshaft. This vibration frequency caused high-strength steel drive shafts to repeatedly fracture and snap at 17,000 RPM. The solution is counterintuitive. Engineers machine the driveshaft diameter down to just 8 millimeters. Purposefully weakening the metal alters its spring rate, allowing it to dodge that destructive resonance frequency. Managing fluid dynamics at 15,000 RPM is a brutal exercise in mitigating mechanical resonance and cavitation to keep the engine from tearing itself apart. Stepping back out to the engine block, the entire structure must still withstand the massive lateral twisting forces applied by the car's suspension. To handle this stress, teams implement a closed-deck cylinder block, integrating the pump housings directly into the casting to act as rigid webbing across the engine. This structural stiffness creates a thermal crisis. A closed deck effectively traps the 2,600 degrees Celsius heat of combustion, threatening to melt the aluminum block. Extracting that heat requires running ultra-thin cooling water jackets, some as narrow as 1.8 millimeters, between the cylinder bores. Traditional metal casting tooling is physically incapable of carving out 1.8 millimeter hollow channels deep inside a solid block of aluminum. Creating these microjackets requires 3D sand printing. Engineers use 0.1 millimeter synthetic sand grains, bonded with hot-cured chemicals, to ensure molten metal cannot penetrate the sand and block the microjackets during casting. Once the mold is ready, they execute an uphill pour, pushing liquid aluminum up from the bottom of the mold rather than pouring it from the top. This minimizes contact with the atmosphere to prevent the formation of aluminum oxide, a ceramic impurity that would create microscopic fatigue points under chassis stress. In a final metallurgical trick, Iron coolers are placed inside the sand mold. These act as heat sinks, forcing the liquid aluminum to crystallize rapidly at high-stress areas to create a tighter, stronger grain structure. An F1 engine achieves its chassis rigidity by manipulating aluminum grain structures and atomic-level sand printing, rather than simply adding thick, heavy metal. Final assembly happens inside an aerospace-grade cleanroom. These highly engineered components must slide together with absolute precision. One speck of dust causes total failure. To survive this environment, parts like the Cosworth pistons are machined to a 10-micron tolerance. Every design choice is a chain reaction of compromises. Aerodynamic demands shrink the block, spiking internal friction, which mandates new pumps, which triggers shaft resonance, requiring new metallurgy to hold the system together. At 15,000 RPM, the modern F1 power unit is the ultimate mechanical compromise matrix. The fully assembled engine block slots perfectly into the carbon fiber monocoque, becoming the primary structural backbone of the race car. The F1 engine is a structural skeleton, a system of mechanical compromises actively fighting to survive the physical contradictions of its own extreme existence.